Okay, so today we are going to take a look at this LeetCode problem 147, insertion sort list. Sort a linked list using insertion sort. A graphic example of insertion sort is like this. The partial sorted list, which is black, initially only contains the first element in the list. With each iteration, one element, which is red, going to be removed from the input data and insert in place into the sorted list. And here are the steps of the algorithm. So insertion sort iterates, consuming one input element each repetition, and growing a sorted output list. So we need to grow the sorted output list gradually. At each iteration, insertion sort removes one element from the input data, finds the location it belongs within the sorted list, and insert it here. So we remove the element from the input data and then find the right location in the output list and insert that data. And then it repeats until no input element remains. So this is the condition where we need to stop the algorithm. There are two examples here. The first example, we have 4, 2, 1, 3 as input. So after sorting, the output would be 1, 2, 3, 4. Similarly, in the second example, after sorting, you can see all the elements are sorted in ascending order. Right. So one idea, I think we can just use the definition here. Every time we just handle one element in the input, and let's take example. So our input is 4, 2, and then 1 and 3. So we are given the header, so we can use the header to help us find the elements that we need to handle. Every time we're going to remove the element pointed by the header and then find a location in the output. So in the output, so this is a common technique we're going to use. We have a dummy node. So when we handle an element, we first need to check whether dummy has a next node, right? Dummy.next, whether it's null or not. If it's null, we know we have reached the end of the output sorted list. In this case, we just put our node at the end. And then we move our header to the right. And then for the second node, right, we remove it from, so this node 4 has been removed. And now we need to handle the next node. The same thing, we start from the dummy node. We check whether dummy has the next node. Yes, it is. At this time, besides checking whether the dummy.next has value, we also check the value between dummy.next and the node we're going to handle. If dummy.next has value which is larger than our current node, we know we need to insert our node between dummy and that node, right? We do it for every node. And now we handle number 1. Okay, we check whether dummy node has the next node. Yes, it is. Then whether the value is greater than our current node. Yes, it is. Then we find the right location for our current node. Right, now we move ahead to the last node, which is 3. Similarly, whether dummy node has the next node. Yes, it is. And then we move we check whether the next node has value greater than 3. If not, we know this position is not the right position to insert our node 3. So we move our node, we can use a pointer, say prev. We move our pointer prev to the next and do the same check, whether prev.next has value that is larger than 3. No, we keep moving our prev until we find, okay, the prev.next value is greater or larger than our counter value. Now we insert that value to prev.next, right? So this is the idea of this definition. Let's code it. First thing first, let's check the corner case. If header is null, we just return the head. And now we need to iterate the input linked list. I think we need a dummy. Okay. If dummy.next is not null, and I think we need a linked list called prev. If prev.next is not equals null and prev.next value is smaller than our current value, which is head, we just move prev to the right, to its next. And then we just check what is the condition that exits the while loop. If prev.next is null, we know we have reached the end. So what we're gonna do is we prev.next, we create a new node. Yeah, that's it, right? Otherwise, we know we need to insert the node here. What we do is, so say we are handling 3, right? And before we insert 3, the output linked is like this. So the first thing, we need to create a value, a node 3, and then 3.next point to our prev.next. And then we prev.next will point to our new created node. So that's the idea. Let's call it temp. I'm thinking actually we don't need to use a new link. We can check later. Okay, temp.next equals prev.next. Prev.next point to temp. And now we just need to return dummy.next. So this is the idea from this insertion sort definition. Oops. Oh, Don't forget to move the head to the next after each iteration. Okay, let's submit it. Okay, so as I mentioned, we may not need to create the temp node. We just use the head node, right? So head, then point to head. Oh yeah, since we can do this because later we're gonna use the head. The head needs to help us keep tracking of the iteration of the input linked list, so we can do this. Yeah. Okay, so there is another solution. That is, we can actually sort the linked list in place. It says in place into the sorted list. So what we do here is, let's just use the same example. So the input is 4, 2, then 1, and then 3. Okay. So the idea here is we're gonna use a pointer, let's say current. Every time we compare current with its next node, if current dot value is greater than its next node dot value, then we know the order is wrong. It's not sorted in ascending order, right? In that case, we need to find a position for its next node. So how can we find that? Similarly, we need to create a dummy node, dummy head. And dummy head is pointing to our input head. Okay? And when we find the current dot value is greater than its next dot value, we need to get this value out, because we need to insert the value somewhere before our current node. But before doing that, we need to link our current node to its next dot next, right? In that case, after removing the node 2, we still can link node 4 and node 1 in this case. And now the problem becomes how we can insert the node 2 into the input list. So we need another pointer. So every time, let's call it prev. Every time we start from the dummy head. Okay? We compare whether the prev dot next dot value is greater than our current value. If yes, then we just find the location to insert our value. We keep doing this until let's see whether it's here or it's the next node. Yeah, since let's go back. So originally it's like this. When we point at 4, we actually is checking whether node 2 has the right position. So when we move the current pointer to here, the last two, right, then we should exit, because when current points at 1, we are actually checking node 3. So this will be a in-place solution. Let's try to code it. If head is null, we return head. Then we need a dummy value, dummy head. Dummy points to our head. And then we need a pointer help us to iterate our input list. Let's call it current. Initially current is at head. And then we need some helper pointer. Let's say list node pref is null. And let's just iterate. If current is not null and current.next is not equals null, okay, what we do is if current.value is smaller or equal to current next.value. Now in this case we know the two nodes are sorted in ascending order. We don't need to do anything but just move current to its next. Else we know the next node, current.next, right, is the one we need to find a right place for it. And we need to first keep tracking of these nodes. Let's say create a node called temp. Temp gonna be current.next. I just don't want to create a node every time. Okay, we keep track of the node where we need to change its location, and then current.next will be current.next.next, or it could be temp.next, right? Same thing. And then we start from our dummy head. While pref.next is not null and pref.next.value is smaller than our temp.value. We move our pref to its next. Once that is done, we just insert our temp into the output list, right? So in this case, we need to insert 2. So how can we insert 2? Our temp.next will point to our pref.next, and pref.next will point to our temp, right? and then we return dummy.next. And let's try use temp.next here. Yeah, same thing. Okay, and let's talk about the time complexity. So for this time complexity, as you can see, for each node, we potentially need to iterate the entire input array, right? Not array, linked list one time to find the right position. So the time complexity will be O(n) squared. And then regarding the space complexity, yeah, so we just have like 1, 2, 3, 4 pointers, so the space complexity is 0(1). Okay, that's it.